Roger Penrose has made a name for himself as one of the most brilliant mathematicians working on physics problems. He has worked on the problems of pure mathematics, quantum gravity, general relativity, cosmology, and the interpretations of quantum mechanics. Due to his famous collaboration with Stephen Hawking, his recent Nobel Prize win, and his appearance on popular outlets, Penrose has become a well-known name in popular culture. I am a theoretical physicist, and in this video we will explore some of the major works of Roger Penrose, and as always I will try to simplify stuff as much as I can without oversimplifying anything.
See these ellipses, and they speed up just at the right time, and there's got to be a mass right at that focus.
But again, it follows on from Mikhail's question. You need equations to tell you how to go from a conformal factor into its reciprocal.
Congratulations, and invite you to receive the Nobel Prize.
Penrose was born on 8th August 1931 in Colchester, in the English county of Essex. He comes from a learned family. His father, Lionel Penrose, was a geneticist, and his mother, Margaret, was a medical doctor. His paternal grandfather, James Doyle Penrose, was an artist, and his maternal grandfather, John Beresford, was a physiologist. When we come to his siblings, we see that his brother Oliver Penrose is a condensed matter physicist, his brother Jonathan Penrose was a chess grandmaster, and his sister Shirley Hodgson is a geneticist. Penrose got a stepfather in 1973 named Max Newman, who was a mathematician and a computer scientist. Penrose started his education in England, but when World War II took place, his family moved to Canada, where he continued his education. Penrose was really slow to learn things, but this slowness gave one of his teachers the wrong impression that he is a bit stupid, and he was moved down a class.
I heard that you were moved down a class, Roger.
I was moved down a class, yes. I think it's when I was 8 years old. I mean, it's a little while back. And there was one teacher who had what was called high grade 2 and low grade 3. I was in low grade 3. And she used to have us do sort of mental arithmetic. You had to add, multiply things. And she was too quick for me. I just couldn't keep up with it. So I was considered to be pretty stupid.
However, another teacher understood that Penrose was just slow to learn, and therefore he gave Penrose as much time as he required.
There was a teacher who I thought was pretty insightful, because I didn't do all that well in the maths tests. But he said, look, I'm going to let you have as long as you like. It was supposed to take the period, and at the end of the period, people had the papers in. Said, take as long as you like. Then I'd do well. I'd get into the high 90s, you see, or 99 or 100 or something on these tests.
He returned to England in 1945 when he was 14 years old and attended University College School in England. Since his parents were associated with biological sciences, they wanted Penrose to be a medical doctor. Penrose asked his headmaster if he could take biology and mathematics, but his headmaster told him that it was impossible. So Penrose dropped biology and took mathematics because he liked math since he was 10. In an interview, Penrose said that this decision annoyed his parents.
So I said, although as I was walking up to see him, I was determined to be a doctor. That was my role, I thought. I said, mathematics, physics, and chemistry. And when I got home, my parents were furious because that was my medical degree, gone down the tubes completely.
He then attended University College London, which was affiliated with the University of London. His father was a professor there, and therefore his fee was waived. Here, he got a first-class degree in mathematics in 1952. For his PhD, he went to Cambridge and started his research under William Wallace Douglas Hodge. Hodge is well known for his contributions to areas of mathematics called algebraic geometry and differential geometry. After 1 year, he switched his advisor to John Arthur Todd, who is well known for his work on algebraic topology. The famous mathematician Michael Atiyah was also doing his PhD in Cambridge at that time, and an interesting anecdote is that Atiyah switched his advisor from Todd to Hodge, which is exactly the opposite of Penrose. Penrose wrote his PhD thesis titled Tensor Methods in Algebraic Geometry in 1958. At this time, he met Dennis Sciama, who was a friend of Penrose's brother Oliver Penrose. The interaction with Sciama had a big part in getting Penrose interested in physics. Penrose also attended lectures on general relativity given by Hermann Bondi and lectures on quantum mechanics given by Paul Dirac.
So I went to 3 talks particularly which had a big influence on me.
One was a talk by Hermann Bondi, on general relativity, cosmology, and then there was a talk by Paul Dirac, one of the founders of quantum mechanics.
Penrose held many different positions before ultimately coming to Oxford. He was an assistant lecturer at Bedford College and later he got a research fellowship at St. John's College. This was followed by a NATO research fellowship for 1959 to 1961 that allowed him to visit Princeton University and Syracuse University. He came back to England to join King's College as a researcher from 1961 to 1963, which was followed by him being a visiting associate professor at University of Austin at Texas. In 1964, he became a reader at Birkbeck College, where he got an assistant professorship in 1966. Finally, in 1973, he got the Rose Ball Chair of Mathematics at Oxford University, and he held this chair until 1999. Currently, he is the Emeritus Rose Ball Professor of Mathematics at the Mathematical Institute in the University of Oxford. His notable students include people like Richard Jozsa, John McNamara, Asghar Qadir, and Tim Poston. The earliest work of Penrose was on a generalization of the idea of the inverse of a matrix. Normally, the inverse of a matrix is defined for square matrices. However, for non-square matrices, we can define the pseudo-inverse, which acts almost like the inverse, but actually is not the inverse. The pseudo-inverse was already discovered by the American mathematician Eliakim Moore in 1920, but it was independently discovered by Penrose in 1955. The conditions that this pseudo-inverse needs to satisfy are now called the Moore-Penrose conditions. Probably his greatest work is his work on singularity theorems. In 1939, Robert Oppenheimer and Hartland Snyder showed that once a big enough star collapses, it is inevitable for it to collapse into a black hole. However, people had reservations about their model because it was too simplified and unrealistic. For one thing, it had too much symmetry. People thought that if they could get rid of the spherical symmetry, then probably this collapse could be avoided. Penrose wanted to eliminate these objections, and to do this, he just tried to prove a theorem by getting some kind of contradiction if the collapse didn't happen. In 1965, he was able to do this, and he showed that some kind of singularity is inevitable in the sense that the space-time should come to an end somewhere. He also came up with the hypothesis called the weak cosmic censorship hypothesis, which says that if you have some singularity, then it should be hidden behind some horizon. In other words, you cannot have naked singularities. When you combine his singularity theorem and the weak cosmic censorship hypothesis, the existence of black holes becomes inevitable. This result was followed by a decades-long search for black holes. In these decades, different evidences for black holes came in, which includes objects like Cygnus X1 and the 1996 study by Reinhard Genzel and his group regarding a black hole at the center of our galaxy. Significant evidence came in 2012 when Andrea Reis and her group found very strong evidence for the presence of a supermassive black hole called Sagittarius A star in the center of our galaxy. This was followed by more conclusive evidence in September 2015 when LIGO detected gravitational waves generated by two black holes. In 2020, Penrose, Genzel, and Reis were awarded the Nobel Prize for their work. Penrose also applied his singularity theorem in collaboration with Stephen Hawking, where they proved that the universe must have started as a singularity if it obeys some reasonable conditions. One of the best works of Penrose is his work on Twistor spaces. Penrose had the idea that instead of the points of space-time, one should consider the light rays as the fundamental objects. When one looks at the sky, one looks at light rays coming from a big sphere. This scenario has some similarity with complex numbers because the complex plane can be mapped to a sphere called the Riemann sphere. This mapping between a plane and a sphere is the familiar mapping that one does to get a map of the whole world on a flat paper. Penrose thought that there should be some formulation of relativity and possibly quantum mechanics as well in terms of complex numbers. Working on this idea, he came up with the idea of Twistor spaces, which is a bit hard to define in simple language, but it is related to the space with three complex coordinates. A simple caveat is that this space is projective, which in simple terms means that any 2 points which are related to each other by an overall factor are considered as the same point. The relation between a point in ordinary space-time and points in Twistor space is established by an equation called the incidence relation. This relation relates a point in space-time to a whole region of Twistor space. This introduces a kind of non-locality in the picture, which is a very interesting feature of Twistor spaces. In an interview, Penrose said that he is most proud of his work on Twistor spaces. Another piece of work for which Penrose is well known is his work on Penrose tiles. Let's take the example of a usual tiling made of squares. We can achieve this tiling by repeating this small square, or this square of length 2, or this square of length 3, and so on. This means that we can achieve this tiling by repeating arbitrarily large repeating units. This is also true if we do it with hexagonal tiles. These tiles are called periodic tilings. A tiling for which we can't have arbitrarily large repeating units is called aperiodic tiling. Penrose tilings are examples of aperiodic tilings. To explain Penrose tilings, we will have to go back to the time of Johannes Kepler. We know that we can't produce a tiling using pentagons only. If we try to do that, we get gaps in the surface. However, in 1619, Kepler discovered that we could produce a tiling with pentagons, pentagrams, and some more shapes. Kepler wrote this result in his memoirs called The Harmony of the World. Kepler knew that these kind of tilings are aperiodic. Fast forward 3 centuries, in 1974, Penrose published a paper called Pentaplexity, where he introduced 3 types of tilings called P1, P2, and P3. These tilings have matching rules to dictate which combinations are allowed and which combinations are not allowed. P1 tiling included a pentagon, a pentagram, a diamond shape, and a boat shape. When these 4 units are put together, we get a tiling like this. P2 tiling includes a kite shape and a dagger shape. These 2 units can be combined to make a rhombus shape, but this combination is not allowed by the matching rules. A P2 tiling looks something like this. Lastly, P3 tiling includes 2 kinds of modified rhombuses, and when they are put together, they look something like this. This P3 tiling is implemented in the construction of the floor of Mitchell Institute of Texas A&M University and the Mathematical Institute at University of Oxford. However, the story of Penrose tiling doesn't stop here. If you move a Penrose tiling in a certain direction, we don't get what we started with. This is a different scenario from a periodic tiling because in a periodic tiling, we do get what we started with. This means that a Penrose tiling doesn't have translational invariance. This property would prove to be very useful later. In 1982, Dan Chechman observed that the diffraction pattern of an alloy of aluminium and manganese was very weird, and a convincing explanation for this pattern was not coming along. With Ilan Black, Dennis Gracious, and J.W. Kahn, he published his paper in 1984 where they tried to explain this pattern using certain types of crystals that had no translational symmetry. These crystals were originally called Chechmanite, but later Paul Steinhardt and Dov Levine used the word quasicrystals in their 1984 paper, which became the standard term for these crystals. The quasicrystals can be thought of as 3-dimensional analogues of Penrose tilings. Dan Chechman got the 2011 Nobel Prize for Chemistry for his discovery of quasicrystals.
The Royal Swedish Academy of Sciences has decided to award the 2011 Nobel Prize in Chemistry to Professor Daniel Shechtman at Technion, Israeli Institute of Technology, Haifa, Israel.
Penrose is also well known for his work on impossible objects. An impossible object is a 2-dimensional sketch of an object that actually can't be a sketch of an object living in 3 dimensions because that object is impossible to exist in 3 dimensions. A person who inspired Penrose to work in this area is Moritz Escher. Escher produced his art piece called The House of Stairs, which was one of the inspirations for Penrose to work on impossible objects. Penrose used to work on impossible objects with his father, and in 1956, he and his father wrote a paper titled Impossible Objects, a special type of visual illusion which included 2 impossible constructions. One of them is Penrose stairs. It seems that you can continue to climb these stairs indefinitely, but these stairs can't exist in real life. The second construction is called the Penrose triangle, which looks like a triangle that could exist in 3 dimensions, but if you look at this triangle carefully, then it is easy to see that it is nothing more than an optical illusion. This type of triangle was already discovered by Swedish artist Oscar Reuterswärd in 1934. Later, Penrose and his father sent their paper to Escher. Escher praised their work, and when he replied to their letter in 1960, he also sent them his work called Ascending and Descending, where Escher used the Penrose stairs. In 1961, Escher also used Penrose triangles in his work called Waterfall. A very controversial set of works that Penrose did includes his work on making sense of consciousness. When Penrose was in Cambridge, he took lectures on mathematical logic by the mathematician Strotenstein. In these lectures, he learned about Gödel's incompleteness theorem and Turing machines.
The other course was a course by a man called Steen, who talked on mathematical logic, and he explained things like Gödel's theorem and Turing machines being the mathematical notion upon which modern computers are based.
In simple terms, Gödel's incompleteness theorem says that if you have any mathematical system which is self-consistent, then you will always have some true statements which you cannot prove using that system. On the other hand, Turing machine is just a fancy name for a computer, and there is a very important problem regarding Turing machines. The problem asks you to find an algorithm to tell if a given computer program will continue to run forever or not. It is called the halting problem because when the program stops to run, we say that the program has halted. In 1936, British mathematician Alan Turing showed that the halting problem cannot be solved. In other words, you cannot find an algorithm that will tell you if a program will halt or not for all possible programs. Penrose said in an interview that when he was taking this course, he came to the conclusion that consciousness is not just computation. Instead, something non-computational is going on to produce consciousness. To back up his claim, he provides an example of a system that is hooked up to a Turing machine. This system has two states which are on or off. If the Turing machine halts, the system is in the off state, otherwise it is in the on state. Since we cannot predict halting, the state of the system cannot be determined by an algorithm, but it is still deterministic because it is determined by the Turing machine. This is an example of a system which is deterministic but not algorithmic. One candidate for a non-computational process is the collapse of the wave function. Penrose thinks that wave function might have something to do with the brain as well. A person who agreed and collaborated with Penrose in this line of work is philosopher John Lucas, and they came up with Penrose-Lucas argument, where they argued against the possibility that something like a human brain can be achieved using a big enough computer. In 1989, Penrose wrote about this matter in his book The Emperor's New Mind, and it received wide and fierce criticism. The number of critical papers on it is just too much for me to show here. Here is a list of papers that criticize the approach of using Gödel's theorem in the way Penrose uses it. Marvin Minsky, who was a computer scientist at MIT, when writing about the quest for scientific explanation, wrote that one can carry that quest too far by only seeking new basic principles instead of attacking the real detail. This is what I see in Penrose's quest for a new basic principle of physics that will account for consciousness. Later, Penrose started to collaborate with the anesthesiologist Stuart Hameroff, and together they developed the idea that consciousness may be caused due to quantum mechanical effects in special structures in the cells called microtubules. The size of these microtubules is of the order of tens of micrometers. They call this model orchestrated objective reduction, or ORC-OR. Penrose wrote about this idea and addressed the previous criticisms in his 1994 book titled Shadows of the Mind. Unsurprisingly, this book also received a lot of fierce criticism. Solomon Pfefferman, who was a mathematician at Stanford, said, "I am personally convinced of the extreme implausibility of a computational model of the mind. Penrose's Gödelian argument does nothing for me to personally bolster that point of view." Moreover, the famous philosopher Hilary Putnam wrote, he describes the hypothetical case of a program that stimulates our mathematical capacity and is assumed to be simple enough for us to understand it thoroughly. There is an obvious lacuna. The possibility of a program we could write down but not succeed in understanding is overlooked. This is the mathematical fallacy on which the whole book rests. However, the strongest criticism was yet to come. In 1999, physicist Max Tegmark wrote this paper where he showed that the neuron firing that happens in the microtubules is at least 10 billion times too slow for quantum mechanical effects to show up, and therefore cognition should be thought of as classical processes. This paper was cited by a lot of critics of Penrose and Hameroff. Hameroff's group retaliated on this paper by saying that Tegmark's paper didn't address the ORC-OR model, but some other model. Moreover, they claimed that Tegmark's results are in contradiction with known results. They were able to reduce the factor of 10 billion, but still all problems were not solved. To resolve these problems, they assumed that the neurons can have multiple states, which are called gel states and liquid states. Using these states, they were able to eliminate the factor of 10 billion that was calculated by Tegmark. Some evidence for the Penrose-Hameroff proposal came in 2014 when Anirban Bandyopadhyay and his group in Japan discovered features of quantum mechanical vibrations in microtubules. Following this discovery, Penrose and Hameroff wrote a review of the ORC-OR theory where they used the Bandyopadhyay's discovery to argue in favor of their model. Another idea that Penrose supports is the idea that there was another universe that preceded our universe. Penrose argues that in the far future of the universe, everything will be trapped in black holes. And since black holes emit radiation, the ultimate fate of the universe is to have lots of radiation in the universe. If all of these particles are massless particles, then the universe should not have any sense of scale. This is because the massless particles don't experience space or time as massive particles do. Since the universe has no preferred scale now, it should not make a difference if we shrink the universe to a smaller and smaller size. The technical jargon for this property is that the universe has a conformal symmetry. Penrose postulates that this far future state of the universe can be thought of as the starting point of another universe.
From each other. The Big Bang is very, very dense, very, very hot. The remote future will be very, very rarefied and very, very cold. But when you squash, the temperature goes up. When you stretch, the temperature goes down. Rarefied remote future is completely, utterly different from the Big Bang, where you've got hot, dense. But when you do this conformal stuff, stretch out the Big Bang, squash down the finish, they're pretty like each other. But the Big Bang is the continuation of the remote future of a previous eon.
This cycle repeats over and over, and this idea is known as Conformal cyclic cosmology, or CCC. Penrose wrote about this idea in his 2010 book titled Cycles of Time. For his idea to work, we have to postulate that the Big Bang singularity is not an actual singularity, but like an apparent singularity. Moreover, the transition from an earlier universe to a later universe should be smooth. A strong requirement for his idea to work is that all massive particles should be erased from existence, because if they are not erased from existence, then the conformal symmetry is not there. To achieve this, we need some process by which all the protons and electrons can decay. However, these kind of processes are not known yet. There are three other contributions of Penrose that I want to mention here. One of them is the idea of a Penrose diagram. A Penrose diagram allows one to see all of the universe in a small picture. These diagrams are used to study black holes. For example, this is the Penrose diagram for a Schwarzschild black hole. This is the Penrose diagram for a charged black hole, which is also called the Reasoner-Nordstrom black hole. And this is the Penrose diagram for a rotating black hole, which is also called the Kerr black hole. The second contribution is the idea of spin networks. This idea uses angular momentum to construct a quantized spacetime. This idea is used to study an approach to quantum gravity called loop quantum gravity. A third contribution is his well-known book titled Road to Reality, which is more than 1100 pages long. This book is neither written at a very popular level nor at a very advanced level. It has 34 chapters, and in the first 16 chapters, Penrose talks about pure mathematics required to describe various topics of theoretical physics. I don't agree with some of his takes in the later part of his book, especially his take on string theory, but a student who wants to read about various topics in theoretical physics with the mathematical concepts that are required to describe them will find this book very useful to study. Penrose has had a lot of success with his works, but on the other hand, some of his ideas are heavily criticized and considered unlikely to hold fruit. Only time will tell if those ideas are accepted or refuted by evidence. However, whatever the fate of these ideas, he continues to be a source of inspiration for a lot of students who want to pursue theoretical physics and applied mathematics. That's it from my side, and I will see you in the next one.